Hi there, my name's Matt Turner, and in this video today I'm going to talk to you about the Unix file system. That is the file system, the set of files and their organization on disk that underpins any modern Unix system. So that's Linux, Mac OS X, Solaris, BSD, etc. So let's dive right in. What is a file system? I don't want to get philosophical. I can't even pronounce it, it turns out. But to me, a file system is data in a namespace. It's a way of, it's a system for filing things, right? So the Dewey Decimal System is a file system, a system of filing things, as is Wikipedia. But every Unix system, needs a set of files to run. It needs its executables, its configuration files, your user documents, and those are all stored in this hierarchy, rooted at the root directory / you can see a part of here that I've drawn out. So this Unix file system is a sort of tree-shaped hierarchy of names of files, of path names or file names, whatever you want to call them, rooted at this / root directory. There's actually a standard for this. It's quite interesting if you're into that kind of thing. If you take a look at it, it kind of tells you what types of files are meant to be in certain places, and certainly a lot of things for me that have been a bit confusing or a bit implicit suddenly sort of made sense when it was spelt out. So if you want to take a look at that, the link's at the bottom of this slide. I don't want to go too much into that. Let's just look quickly at how one of these file systems is put together. So this hierarchy, starting at / is built up through a system of mounts. So I guess the name file system is a bit ambiguous, a bit overloaded. What I'm talking about here is every file name on the system, starting at / and going from there. Every piece of data that's accessible via a file. The other sort of common meaning of file system is a formatted disk, if you like, right? The particular implementation, like an ext4 or a FAT or an ISO 9660 on a piece of media that can be inserted into a system and you mount it on that system. So that has a file system of a particular type, and then file system can also mean the file system driver, the actual code that implements the ability to read and write that file system, because all the different types all look different on disk. But they all come together to make what's sometimes called the VFS, the virtual file system. This layer of file names accessible to every process in a Unix system, starting at the root directory and going out from there. So the way you build that view of all the files you can access on a system is first of all by mounting one sort of root file system at /. You can see on this system, that's the dev VDA device, specifically the file system, the ext4 flavor file system on that device has been mounted at root at /. So this is an actual disk in this system. It's got all the files from my Linux distribution on it, so the thing can boot and run. And from there we extend that tree by mounting more file systems over directories from existing ones. So in this case, this root file system contains a directory called /sys, and I've mounted a sysfs over the top of it. These are actually all sort of virtual file systems, which is something I'll cover in part 2. Sysfs, procfs, udev, they don't have disks full of actual data backing them. The files that they offer up to the users of the system are actually sort of generated on the fly in memory. That's a more modern but entirely legitimate use of sort of files and paths that, as I say, I'll cover in part 2. The eagle-eyed amongst you might have noticed that this isn't a real machine. It's a VM. You can tell that because it's dev VDA, not SDA or HDA. Again, something I'll cover in part 2. But this thing, it doesn't have a disk array. It doesn't have a CD-ROM drive or a USB slot I can plug a stick into. It just exists in somebody's cloud somewhere. But nonetheless, it has this hierarchy of files that we can read and write and interact with that are built up by mounting the root disk on / and then by mounting other file systems of various types over directories that already exist. But today I actually want to just focus on the sort of the file names and the files themselves, and what they actually are and how they actually work. So here I've got sort of 3 names plucked from the file system at random. bin vim, which is an executable, right? The vim editor, etc shadow, which is the file that contains all of the passwords for all of the user accounts. and var run cron.pid, which is a PID file. So it contains the process ID of the running cron process on this system, so that other instances of cron can find it and interact with this one singleton. This is more of a sort of temporary, ephemeral file. This probably wouldn't exist in long-term storage when the machine was shut down. It's kind of written when cron starts a boot and then deleted when cron shuts down at shutdown time. But again, it's a totally legitimate use of the file system as a way to store, sort of persistent information. So these names are just names. They're actually links from the file system, from this sort of namespace of paths to the actual data. But how does that work? So the actual data on disk are sort of logically, one big block, one long string of characters, of bytes that you can interpret however you want. Realistically, they're actually going to be a collection of blocks or extents or something. Management of those blocks on disk, especially allocating and freeing them, is hard, and is a lot of what an actual file system, the actual code of ext4 or ZFS or something, spends a lot of its time doing. But if you just assume that we've got these strings of bytes or blocks of storage, however you want to look at them, here that contain, vim is an elf executable, so it starts with the 3 characters elf to identify that type of file. Etsy Shadow's got super secret hash passwords in. Var run cron.pid has just got an integer with a process ID. If you take a file to just be a big contiguous block like that, then one of these names is just a link pointing to one of those files. Except it's not on a Unix system. On a Unix system, there's another layer of indirection in the middle, a data structure called an inode. So this inode contains the metadata about that file, the number and the size and the mode and the links, all of which we'll come to. And it also contains that list of blocks or extents where the data are actually stored. So that's not shown here, but there'd be some potentially fairly complicated data structure listing all the actual bits of the disk you'd have to put together, in a certain order to get the string of bytes that make up these files. So each one of these inodes has a number that identifies it uniquely. That's an important point that we'll come on to. It has a size, which is the content, the length of the contents of this file. It has a mode, which is 2 things. The first 4 bits of that tell you what type of file it is. So sort of regular files, they're called, normal files, which all of these are, files that just contain data that can be read and written. They're actually only one type of file on a Unix system. Symlinks are another, directories are another, pipes, sockets, block, device files. We'll come on to all of those again in part 2. The mode also contains, as I say, that type indication is in the first 4 bits, and then the rest of the mode contains the permissions, which you may have heard called the nodes. So read, write, execute permissions for the user, the group, and the world. So the number, as I say, kind of uniquely identifies the inode. If you look at this inode on the left, it is not really bin vim in any moral sense. It is a block of data on disk that, in this case happens to be a valid elf. So if you've got something that understands elfs, like say the Linux kernel, it can execute that elf. So it is a file. It has some metadata like a length and some permissions, but that name, vim or bin vim, is not stored anywhere in that inode. All that's stored in that is the inode number, which is its sort of uniquely identifying key. And this is important, and we'll come to why that's important later. What's also important to note about these inode numbers is there's one number space per file system, right? So on any the disk that's running this Linux system, the hard disk that contains the distribution, all of the numbers for all of the inodes are unique. That's how they're identified. If I plug a USB stick in with another ext4 file system on, there's nothing to say those inode numbers won't clash, because how that stick could have been formatted and written to on a different system. How would it have brokered those inode numbers? How would it have made numbers that are never going to clash with any system it's plugged into? So inode numbers are unique only within the file system that they're a part of. And again, that becomes important. So I called these names, these paths, links. they are. That's their technical name, but the more common meaning of link that you might have heard of is this. It's a symlink, short for symbolic link. This is actually just another file with a special mode saying that it's a symlink, but we'll come on to that. What this file contains is a path, right? So its contents, instead of the actual contents of the documents, are just a path to another file. This path can be relative, in which case it's interpreted relative to where the symlink lives, or it can be absolute. So here we have a bin vi symlink, a compatibility thing, pointing to bin vim. So a few things about this symlink. It can cross file systems because what the symlink contains is a path, right? So that path can be anything, and it can point to any path on the system, which of course, as we know, could have come from any file system mounted over any directory in that hierarchy. So these symlinks, they're really not very special. They're just files that are interpreted in a certain way. So there's nothing in them that stops their target from being deleted, right, or its entire file system from being unmounted. So here we have bin vi. It's a symlink. It points to bin vim, but if bin vim it gets deleted, or the file system it's on gets unmounted, then that bin vi, if you try to access it, will result in an error because its target's gone away, and bin vi had no way of knowing that. It had no way of stopping it. So as I sort of said earlier, these things are actually just normal files. Well, they're not. They are files. They're not regular files in quotes. They're a different type of file. So their mode field contains a different set of bits, saying they're a symlink, not a regular file. So they're shown differently. They have an L right at the start. If you do an ls-l, that L means link. So what's actually going on is this. So there is a name, bin vi, that is a link to an inode. That's got an inode number. It's got a size of its contents. So in that case, that's going to be 8 for /bin/vim, maybe 9. There's maybe a null terminating character on, like a C string. I can't actually remember. The mode has normal permissions on, access permissions, but also has the bit pattern that means that this is to be interpreted as a symlink. So this is not a document, a text file whose contents are bin vim. This is a symlink. So you look at the contents of it and you interpret that as a path in the system. If that's not a valid path, or if it points to something that doesn't exist, then you've got an error. But it's meant to be interpreted as a symlink. So this is how it will actually sort of look on disk. So the other type of link, something that you may have heard of, is called a hard link. Now what a hard link is another name that points to a pre-existing inode. So in this case, bin vi is not a symlink to vim. It's not its own file that contains the contents bin vim that's then interpreted in a certain way. It is actually, just like bin vim, it is just another link to that inode. So vim is an entry in the bin directory, and what directory entries contain really is the name, so in this case vim, and then the inode number of the inode that they point to. vi is another entry in the bin directory. It's another name, a different name, with the same inode number. So that inode on the left, like I said before, isn't really morally bin vim. It doesn't know the name vim. It's no more bin vim than it is bin vi. Both of these have sort of equal right to it, if you see what I mean. Both of these point to it. The text I've pasted in at the top here is an ls-l for that vim. And that second field there, that number 2, you very rarely see a number 2. The number 2 there is that link count from the inode's metadata. So that's being rendered out by ls-l. And what it's telling us is that inode knows that there are 2 links that point to it, not one. So one of them is bin vim, which is what we've listed here, and the other one is bin vi. So if we did an ls-l of vi, we would see, vi, it might have a different date on it because it might have been made at a different time. It might have different permissions. It might be owned by a different person, but it's also going to have a link count of 2. So file names aren't the only things that can have references to inodes. When a process is running, it's going to need to open files. This is maybe a slightly weird example to give, but of course it happens all the time. This is a copy. PID5 here is a process that's this copy of Vim that's running. So every program that's running, needs to have its actual binary file open so it can read the machine code that it's going to execute. Equally, PID5 could have another link to the inode on the right of this slide, because it could be opening via run cron.pid as as a document. So Vim is an editor; you could be editing, that file. In either case, the running process ID 5 has a reference to the inode, so it would open via run cron.pid for for editing with the open system call. It gives that a path, but the first thing the kernel does is it looks that it goes and finds that entry in the directory, follows that link, gets the inode number, and then the process has a link to the inode. No longer through that path, and we'll come on to why that is. But yeah, in this case, PID5 actually has one of the potentially many files it has open is bound to be the binary that it's actually executing. So if you saw there on the right, the name via run cron.pid actually disappeared. So if I want to delete a file, I sit at the the CLI and I type rm, short for remove, or I delete the file, as it were, in quotes. But if you think about it, what's the system call for that delete, for that rm operation? What is what system call do you call if you want to programmatically delete a file? What system call does rm call if you strace it? The system call is actually called unlink, and that's very telling because when you delete a file, what you're deleting is that name. You're deleting that entry in the directory, and that removes a link to the inode. And these inodes are reference counted. That's what the links field does. So ls-l or stat will tell you the number of links. So in this case, as is sort of normal for files, var run cron.pid, the path was the only link to this inode. So we said rm, that called the unlinked system call, that removed that link. And because this is reference counted, now there are no links to it, it dies. So now there's a bit of space on the right hand, in this slide. We can see that there's lots of ways in which there can be lots of open handles to a file. Like I said, any other program could have opened bin vim via open just to edit it as a document, because it is just a file at the end of the day. It's not magic. It just happens to contain machine code if you squinted it in a certain way, which the kernel's sort of execution mechanism knows how to do. In this case, PID5 forked made PID6. Across that fork, that inherited the file handle that it got a copy of the file handle that PID5 had. There was no call to open in this case. It was fork that caused the duplication of that file handle. There's lots of system calls like dup will duplicate a file handle. M-mapping things make new references. So my point here is that there's lots of different ways in which processes can end up with references to files. And of course, you can have one or more hardlinks from the file system as well. Well, 0 or more is actually the point I'm going to make here, because I can, PID5, PID6 are both running copies of Vim, but I can come along and I can rm bin vim, so I can remove that. I can remove that name, unlink that link, but there are still 2 links to this inode. So again, the reference counting means that it lives. PID6 can then quit, but PID5 is still executing, and then when PID5 finally quits, that's the last link. And the file is actually deleted. So the space that inode was taking up on disk, that metadata structure, and the actual blocks of the file itself are all reclaimed by the file system code. So as one final sort of example of this inode system is why upgrading software on a Unix system, on a Linux or a Mac system, doesn't suck, right? So imagine I have a copy of Vim 8 installed. Bin vim is that file. Bin vim, as we now know, is just a name that points to an inode, that points to the blocks containing the Vim8 binary. And it's also currently running as PID5, so process ID 5 has that inode open. It was run as /bin/vim, but then the lookup was done to the inode number and the handoff was made. So what PID5 has in its file descriptor is an inode number. I can install Vim9 by downloading its binary files, its executable, to my disk. I can then delete the old bin vim name and reuse it, so I can make a new entry called vim in the bin directory that points to a new inode. Although, you can think of that as, changing the inode that was in place, maybe keeping the same number, but just changing the blocks it points to. That you can do one or other. There's various reasons why you won't want to do either. But all in all, we now have a name vim in the directory bin that points to a different inode with a different number that points to the Vim9 blocks. And this can all happen while Vim8 is still running and can continue to run, because that old inode number, still exists because there's still a reference to it. I just happen to have made a new one, and I've removed the old link that pointed to the old one, and I've made a new link that points to the new one. Just happens to have the same name because morally it's the same thing, right? So when that last copy of Vim 8 quits, last link to the old inode goes. Old inode is garbage collected or reclaimed or finally freed, or however you want to look at it. And then the next time I run Vim, I'm getting the lookup done for that new path. I got the new inode, and I'm using the new Vim 9 binary. And you can't do that on Windows, certainly. The reason for which is that when you get to this stage here, and because there's no inode in the way, Vim is a direct link all the way down to those blocks on disk. So if Vim wants to continue to exist, it has to go and change the actual binary, but that binary is running. So you can't replace the file while it's in use by something else. But if you add this layer of indirection here, then everything works swimmingly, and the Unix file system is great. So thanks for listening to this video. This was part 1 of my introduction to the Unix, Linux and Mac OS file system. Hopefully this has been enlightening, and you now understand what terms like symlink and hardlink and unlink and inode when you've heard them. In part 2 of this video, which I'll post shortly, I'm going to look at the different types of files, so directories, symlinks, but also device files, named pipes and sockets. I'm going to briefly cover, you may have heard people say everything is a file in Unix. That's a sort of philosophical statement, and there's some nuance behind it. So I'll just go through what that means and what implication this sort of inode based scheme has on that as well. But thanks for your time today, and I hope you found this useful.